All right. So today we have a treat. We have my good friend Yishay Carmiel, CEO and founder of Meaning.team. Tagline is make each conversation crystal clear and a real-time generative AI solution that harmonizes communication. But for the purposes of this podcast, we won't be talking that much about meaning. This is really about generative AI in the context of voice. So a lot of us use generative AI in the context of large language models, the text in, text out. So a lot of what Yishai will be talking about will be voice in, voice out, but in real time. And for our audience listening to this on a podcast, if you want to follow along, so Yishai will actually be showing slides during this presentation. So if you want to follow along to the slides, go to the YouTube version, which you can find on the episode notes, which is at our website, thedataexchange.media. And with that long-winded introduction, take it away, Yishai.
Well, it's a pleasure meeting you, and it's great to have this conversation with you, Ben. And feel free to ask any questions during the presentation, because again, as we said, this is a conversation. Just to give you some background about what we're doing and background about myself. So I've been in the voice space for more than 15 years now. I've been experiencing all the phases of what we call speech. So basically, I built speech recognition systems back in the days, when we'd call it statistical machine learning, then started working on applied deep learning for speech recognition, then analyzing human conversations. And then in the last few years, I've been working on generative AI for voice. And one of the things that I'm really, really excited about is that, usually these times are actually where things are moving in some kind of exponential way. Just to give you some kind of a background of what we are doing in Meaning, and again, I don't want to go into very details about our stuff, but we have some kind of a thesis that human conversations are going to be augmented by AI, and specifically by generative AI. And what do I mean by that? Do not mean that, for example, that we are going to analyze conversations, but basically what we are going to do is that our thesis is that I can take my voice or any person's voice into that matter and literally convert it into another stream in real time. Let me just show you some kind of a very quick demo, and then we can deep dive into the really cool stuff about.
Before you play the demo, explain what for the podcast listeners, explain what they're about to hear.
So basically, Meaning, one of the things that we are doing, we are doing speech to speech, and I'm taking my voice and I'm converted into another voice in real time. So one of the things that we are doing over here, we are doing an accent conversion and a voice transformation. So basically, as you can hear from my accent, I have a very thick Israeli accent. I'm not trying to hide it or anything like that. And in the demo, and again, just for the sake of that, we just recorded a very quick demo just for you to see how the system is working in real time. And this was an actual recording of a live Zoom conversation. Sure thing. So let me just share my screen. So one of the things that we've built a very powerful technology that enables us to transform any person's voice into a target voice avatar. So this is Daniel. Daniel is a person, he's an actual person. He was born and raised in the US. He's based in Baltimore. And without further ado, let me do.
And now, I'm not if you know, I'm still shy, but I'm not speaking with my take heavy Israeli accent. I'm speaking as downhill, hopefully where you can enjoy my American accent right now and we can have a live conversation. Maybe I can give a little bit explanation about the LLM technology. Riza said we have a very, very powerful novel that does in real time voice and accent conversion. And basically we train these neural network that it knows how to take any type of voice, regardless of the accent, in terms of even my and Israeli accent, and convert it into a target speaker. In this case, it's Daniel.
Amazing. And it's back to my voice.
So then quick question, Yishai, a quick clarification for our listening audience. Yishai was talking and it was in real time converting it to another voice, right? And so obviously listeners probably have heard about this notion of deep fakes, where you take a voice and then kind of on a batch level convert it to another voice. But this is actually happening in real time. And don't worry, we will talk about ethics towards the end of this presentation. So we will table the question of deep fakes for now.
Yes, exactly right.
Next.
Sure thing. And now I want to talk a little bit about like what's going on in the voice space. And I think that it's not just happening in the voice space, it's happening in every type of data medium that we're seeing. And again, one of the things that we are seeing in the past 2-3 years, we are seeing some kind of a transition between what we call analysis. And when we are thinking about starting applying machine learning, and I'm going to take speech as a context, we analyze speech. Basically, we transcribe that. We try to find like meanings inside the transcriptions. One of the things that we are seeing is that we are moving into what we call synthesis, generating new things. For example, we can generate images, we can generate text, and especially we can generate, of course, voices. And as you can see in a previous demo, we literally generate a new type of voice using generative AI for voice. And again, as I said, Ben, I've been in the voice space for quite some time. And to be honest, I'm just going to give a little bit of a disclaimer. Usually I'm putting these slides every time because I'm trying sometimes to convince the audience that why speech is important. But fortunately enough, in the past few months, OpenAI and a lot of other companies did all the work for me. And basically right now, like we see that, sorry for that, that voice is such an important medium. And I think that the first thing that we are seeing, and we saw that with GPT-4o, is that it created a new way to interact with machines. And basically, this is what we call speech-to-speech. Basically, we saw a very, very set of impressive demos that you can speak to the machine, and the machine is going to answer back with two underlying technologies. And again, we have, of course, GPT as the core engine that tries to analyze the text. But basically, we have a speech recognition system, for example, like Whisper, that tries to transcribe and analyze what the user is saying. And we have a speech synthesis that sounds very, very natural, very, very emotion. And I even saw some articles that people actually are bonded and are really connected to this system because they are thinking it's like a human being.
Hey, Yishay, so one scenario I wonder if this is in the near future is the following, right? So you go up to your appliance, let's say it's a smart refrigerator, and rather than consulting the user manual, you just start talking to your refrigerator, and your refrigerator will do some kind of local retrieval augmented generation and then tell you the answer.
You're spot on. Because if you're thinking about it, like this is one of what we call the holy grails of speech-based interfaces. We as humans are very feel natural to speak to each other. So when you're thinking about machines or robots or any types of AI, the most natural way for us humans to communicate is to talk to them. And instead of getting text back, is just for them to talk us back.
Because in that scenario, you can imagine, the user manual is usually just some sort of PDF file. It can start with that PDF file, and then if you're not satisfied with the answer, you ask a follow-up question, and then now if it's connected to the internet, it can go to the other databases that the appliance company has, right?
Exactly, and you can even create some kind of a dedicated LLM based on the user manuals and FAQs to even even be more helpful for you. So yeah, so the answer is that if you're thinking about it, this is one of the things that that people are really, really excited about, what we call voice agents. And the other thing that we are seeing, and I won't say that we are starting, we're actually seeing that, is that music and audio are playing a very core part of a lot of what we call content generation that people are generating right now. Think about the videos, think about games. Right now, for example, generating new types of music is becoming something very, very interesting. So again, when I'm talking about speech, again, this is what we're dealing, but usually speech and audio are very correlated with each other, because basically what we are trying to do, you're trying to generate a one-dimensional signal audio from some kind of an input text. So yeah, so that is why when I'm referring to voice, I'm not just referring to speech, I'm also referring to what we call how can we generate new type of content. And I just want to give some kind of a glimpse about when we are thinking about speech. There are three core pillars of technologies that we can think about. Okay, and again, so the first core pillar is what we call the most natural one, is what we call speech recognition. Basically, a system that when you are speaking, it tries to find what are the words, to transcribe what are the contents that you've said, and convert your speech into text. And this is like what we call the classical speech recognition. Has been developed since the 1950s. In the past few years, we saw a tremendous quantum leap forward into these type of systems. Some of people are actually saying that these technologies are so popular and so good that they are becoming a commodities. And
Yeah. So you would say, for example, Whisper is in this category.
Absolutely. And again, like Whisper is some kind of a speech recognition. And again, and for every type of technology, it has its quirks and it has its challenges. Are we dealing with real time? How can we optimize it? How can we scale? And how can we make it more robust, to various accents and to various noises? But generally speaking, the technologies are evolving in a phenomenal pace right now. The second type of technologies, and again, it's called what we call speech profiling. And I would describe it as everything that you are trying to get from speech, which is not a speech recognition or speech synthesis. Basically, for example, if I'm speaking, can I detect the language? Can I detect my age? Some of the things that are very, very interesting right now is that based on speech, people are trying to predict if you have some kind of a disease. For example, back in the 2020, 2021, there was some kind of researchers and scientists that try to predict if you have COVID based on how you speak and how you're coughing. So basically, this is what we call speech profiling.
So in the future, speech profiling would also include detecting whether or not this is an artificial voice.
Absolutely, and this is one of the core things. And again, you're spot on. Then, so basically, to detect if this is a real voice, if this is a deepfake voice, and a lot of these things are under this category. You're spot on. And the last thing is that this is the core pillar of this talk is what we call speech synthesis. And one of the things that we were saying is that giving some kind of a text or some kind of information inside some kind of initial information, how can we generate speech? And this is like the most thing that I'm going to address in this conversation today. And the things that I want to cover in our conversation is, first of all, the most basic thing: how do you generate speech? Okay, and what are the core technologies behind what we call generative AI for speech? The second thing, it's interesting, and speech also have its type of LLMs, and basically speech scientists took the core pillars and the core interesting aspects of LLMs and applied that for speech. And I can say that it created some very, very interesting and groundbreaking results in terms of that. And as we discussed, the last thing that I want to address, because a lot of these things are related to ethics and safety, and we need to make sure that, first of all, I want to make sure that we are covering that, but these technologies are evolving in such a fast pace that we need to address that, and we need to create some kind of very, very sufficient security measures in order to deal with these type of technologies. So let's talk a little bit about generative AI for speech. And the first thing that I want to cover is that if you're thinking about generative AI for speech, of course, the most natural technology is what we call text-to-speech. Is basically you have some kind of an input as a text, and then the system output as speech. And if you're thinking about it, a lot of the technologies that we are familiar today are using what we call text-to-speech. Okay,
And
but one of the
one observation, Yishay, this seems to have gotten cheaper and better in the last year.
It's gotten cheaper and better in the last year for sure. It's also got faster, because one of the things that, if you are thinking about it, in order to create what we call voice agents, you need to make sure that these systems are with very low latencies. Because again, like
How worried should you be if you're a voice actor?
I would be very, very worried.
Because my experience with this is usually for articles. So not the articles is fine probably, but maybe a book. I don't know. I haven't tried it. I haven't tried these things for a book. Yeah.
It's great for books. So here's the thing. Let me just rephrase it. I think that one of the things that we're seeing is that as a voice actor, and again, I do want to address this question. You have a certain type of voice that can be used for commercial applications. One of the things that is happening right now is that, okay, there are two options: either that I do not need voice actors, or voice actors, on the other hand, can leverage that, because if they're looking at their voice as some kind of a core asset, they can have they just leverage some kind of a very smart and efficient distribution channel to distribute their voice in a much more efficient way. Up until now, for example, a voice actor would need to go into a studio, and they were limited by the amount of that time that they can invest. Now they're not limited. If you have some kind of a core asset, you can leverage that over and over again. So it really depends, going back to your question. If we're talking about the other type of technologies that we have multiple more. We have speech-to-speech, which is basically what you've seen in the demo, taking my voice and convert it into another voice. And there are different type of technologies under that. There's voice conversion, accent conversion, translation, for example, speech-to-speech translation, which is something that is very important. And you have something that is called style transfer, which sometimes, again, it's very related to voice cloning, because sometimes I want to have a text-to-speech system saying something, but, for example, Ben, in your own voice. So basically, the input for such a system is a text, which what I wanted to say, plus a sample of your voice, and then the text-to-speech systems knows how to clone your voice and to say that. So this is what we call style transfer or voice cloning system.
So the style transfer or voice cloning at this point, for a decent result, how much sample voice should you have?
It really depends. So based on the papers, and again, based on the papers, and I can say from between 5 to 15 seconds, which is quite shocking and quite disturbing, to be honest. It really depends, but I would say that it's 5 to 15 seconds, not on every type of voice. If your voice, for example, is very noisy, or if your voice doesn't have a lot of speech, it will be hard to mimic that. But if I have some kind of a good, decent recording, with 5 to 15 seconds, then I can create a very good voice cloning of your voice based on the recent technologies.
So it's fair to say, if you have a minute, that would be an excellent result.
Yes. And as you can imagine, this is not quite disturbing. This is very, very disturbing from a lot of aspects.
Mm-hmm.
The other two things, it's what we call text to music. And we are seeing that these type of very, very cool applications that I can generate some kind of, given some kind of a prompt, I can generate music. And the last thing that is starting to gain some kind of an attention, it's what we call speech, and it's what we call single synthesis. So basically, I can say maybe it's speech plus text, that I can literally sing something plus text, and it will create a whole melody and a music based on my voice.
Yeah. So what about how far are we from the text plus speech output is music? So in other words, here's some instructions for what I want the song to be about. Here's 20 seconds of Ben saying something, not singing something. And then the result will be an original song sung by Ben based on the instructions.
I think that, to be honest, I think that the underlying technology is there. You just need to put all the parts together. Yeah. Yeah, and one of the things that again, based on me experiencing the industry, these things are moving so fast that any type of prediction that I will give you will probably like be faster than that.
But you'll need, if you do this, you'll need some kind of service that allows you to, okay, so here's the resulting song. I want to check it against a database to make sure I'm not violating any copyright. Right?
So, by the way, that's one of the things that is happening right now with all the text to music. And there have been a few lawsuits against some audio, like some very well-known startups in this area, that have been sued because of that. And so again, it's a very debatable matter of do they infringe or not infringe. But again, that's something that is beyond my knowledge and beyond my scope. So I just want to give you a glimpse, Ben, of how what's the block diagram of a text-to-speech systems. And again, if you're thinking about the three core pillars of a text-to-speech systems, again, we can think about, you have an input text, okay, and this is, to the left of us, and the output of the right is some kind of a speech. And in the middle, you have basically, if you can think about, you have like three main blocks. One of them is what we call the NLU, some kind of an NLU agent that knows how to take the text and compose it into some kind of a basic building blocks. And I will, like in the next slide, I will give some kind of a high level information of how we are doing that.
But this is natural language understanding, right?
Yes, some kind of a natural language understanding engine. It's much simpler than some kind of a very high, cutting edge LLM, but it's some kind of a natural language understanding system that knows how to take text and decompose
So
it.
basically here, the text is like a prompt, and then the NLU will analyze that prompt.
Yes, it will analyze that prompt, and most of the times text-to-speech systems, they are working on some kind of a basic building blocks, which are called phonemes or some other characters. So they, this NLU will know how to decompose them into phonemes. So that's the whole core of the NLU engine. Then the second thing is what we call how to text this text and convert it into basic units of sound. Okay, and these units of sounds are not in what we call the time domain, they are in the frequency domain. And as you can see, there is also some kind of a block that is called prosody modeling that also tries to predict, for example, the emotional, how to generate that and how to make sure that it doesn't sound very flat, it sounds very natural. And then on the right, you have some kind of a system that is called vocoder, which knows how to take these basic unit sounds and convert them into some kind of a signal, into what we call a time domain signal. So this is what we call the vocoder. Back in the days, when I'm saying back in the days, in the 2016, 2017, 2018, even like up until 2020, I think, you would train, for example, the vocoder, the NLU, and the what we call the text-to-melt, the text-to-sounds, as like three different type of neural networks. And in the past 2 or 3 years, maybe even 4 years, you have what we call end-to-end speech synthesis systems that basically tries to compose all the things together, almost all the things together into some kind of an end-to-end neural network.
So a few years ago, when we talked this end-to-end speech approach, you described it as a little more kind of experimental at that point. So you're saying now today, this is what's being rolled out.
Absolutely, yes. A lot of these things, and again, a lot of these things, it really depends, but a lot of these things are composed in some kind of an end-to-end or very close to end-to-end systems. So Ben, as I promised, let me just touch base about the core thing of the things that are needed in terms of the NLU. And the main reason that I want to address that is because some of the things sometimes, again, when you're building a text-to-speech systems, you know that these things are super important, but sometimes it seems very natural or unknown if you are not. So think about for example, the following sentence. My email is abc@gmail.com. Okay. So basically, we know as humans, we know how to pronounce it and how to decompose it into the following text. But if you're thinking about some kind of an NLU, it needs to decompose it. This is what we call text normalization to the following. My email is A space B space C at the word at gmail.com. Okay, so basically this is the input that that needs to be entered into some kind of a text-to-speech systems. And again, you have so many examples. So think about, for example, just the number one, the digits 1939. Okay, so I can say my father was born in 1939. Okay, and these digits represent some kind of a pronunciation. I can say please press 1939, and I can say this computer costs $1,939. Okay, so each time we need to have some kind of a different type, and you have so many things. Think about, for example, ST dot. It can work. It can present saint, and it can present street. Okay, so you have a lot of these type of abbreviations and acronyms and different type of things that you need to teach your NLU how to properly pronounce it. And we as humans.
So the people in this space, Yishay, they must have data sets that have all sorts of examples, right?
So back in the days, again, in what we call the statistical machine learning, you needed to build like a huge amount of data sets and what we call rules and exception rules to do all of that, and people will evaluate. But right now, it's becoming much easier because again, you can create some kind of an LLM, or you can create some kind of what we call a machine translation that knows how to do that. And basically in the web, you have all this information. So again, if you're thinking about it, like back in the days, it was very complicated task to build like a very, very good text normalizations. Now it's becoming much easier. It's becoming also what we call a commodity. And also, just for the listeners, I want to touch base a little bit about how what we call the core part of a text-to-speech system is working. And again, the listeners are more than invited to look to look how these systems work. I'm just giving you some kind of an example of a well-known architecture, which is called WITS. Okay, and again, I don't want to go into the very, very specific details, but if you're thinking about it, in order to generate some kind of a system that knows how to take parts of text and convert it into part of speech, it needs basically aligned inputs of what we call a part of text and part of speech, train them together. One of the things that is happening, and this is happening a lot in what we call time that one-dimensional times that is moving, one-dimensional signal that is moving into time, is that we need to align these things together. So we need to create some kind of a predictor that knows how to align or how to match these specific text or these specific units of text into this specific part of speech. So we have some kind of an aligner. You see that this is like this matrix with the white and black circles in the middle. So they have some kind of a dynamic programming algorithm in the middle. And again, it has some kind of a neural network that has a decode that has some kind of encoder to the part of speech. It has some kind of an encoder that encoder for the part of text, knows how to match them together, and have some kind of a predictor network. This is basically the core architecture, and the listeners are more than invited to look on huge amount of tutorials to give some kind of a deep dive into these architectures. The recent architectures are based on cooler algorithms like diffusion models or more advanced algorithms, but this is the core architecture that people are using today for text-to-speech systems. And so where are we right now in the terms of text-to-speech? So I think that the things that are working really well, and you see examples. So avatar dubbing, podcasts, if you want to generate podcasts, if you want to do translation, you see, for example, companies like HeyGen, DeepDub, 11 Labs that are doing dubbing, and you can do translation and generate voices in different languages. This is working really well. They can serve as input for voice bots.
Most of the companies who do this are not real. They're not doing it in real time, right?
So if you're thinking about text to speech, it really depends how you define real time. So a lot of I think that the standard for companies who are doing real time is
text to speech. Yes,
yes, text to speech. So usually you define real time is less than 400 milliseconds of latency. So basically you want that the text to speech will start generating voice, in less than 400 milliseconds. And sometimes you even you have some tricks to stall the system, so the system can say, "I got it," or some kind of well-defined prompts that that gives the user some kind of illusion that the system is interacting with you until they know that the speech is generated. So this is working really. These things are working really well.
So have you seen a system that doesn't make mistakes? In the sense of if you have a reasonably competent human reader, they can read through something and know how to read everything, right? So like they're not gonna mess up the 1939 1939 example that you gave. A lot of the free services that I use still mess up a few things.
So you're spot on, and this is, and we can call it hallucination in some sense.
Yeah.
Okay. So if you're thinking about the next evolution of, and again, when I'm saying the next is these things are already very, very good technologies. I think zero shot is we talked about 5 to 15 seconds of cloning. The question is that can we create systems that have better zero shots, even if the recording is not at the best? Or, for example, I have a text-to-speech system that was built in English, and I'm Yishay. I have pretty thick Israeli accent, so can I create a system based on 5 or 15 seconds of my voice that will mimic also my accent? So that's what we call zero shot. And stability. So there are a lot of examples. Again, if you are taking a text-to-speech systems and you're spot on, Ben, is that I'm injecting some kind of a very short prompt or some kind of a well-known prompt, it will generate a speech without any problems. But for example, there are all these, for example, if I'm pressing writing 20 times 9, sometimes the system is getting out of whack in some sense. It will miss a word, or it will not write. It will just create some kind of hallucinating information. So some of the papers are talking about, and Microsoft came out with some kind of an interesting paper that the system is much more stable. They gave some interesting examples of instability of previous systems and how the systems are more stable right now. So this is another interesting topic. Of course, injecting more cutting edge architectures like neural encoders and neural compression algorithms. This is something that is gaining a lot of attention. And I think that one of the interesting things that is gaining is also what we call latency, improving the latency of the system.
And also, I guess, Yishay, in my case, my main use case for text-to-speech tends to be magazine articles or newspaper articles. And so the challenge for these systems in that context is freshness, in the sense that there might be certain words in pop culture or memes where maybe it wasn't in the training data, but now suddenly we all know how to pronounce these things because we read the news, but it's not yet familiar to the system, right?
But over here in the NLU part, and this is something that you have something that is called graphem to phoneme. We have these type of algorithms that I try to pronounce based on what we call try to read in some sense the type of words. So you have it.
But it might be, I don't have a specific example, but it might be something that just came up yesterday, and we all know how to pronounce it, but the system won't, right?
So the system usually there is an algorithm in the NLU part which is called graphem to phoneme, which basically knows how, given some kind of a characters, knows how to, the phonemes are how you pronounce the words. So it knows how to convert, the characters into some kind of a pronunciation modeling. So that was even built.
But it might not be the way, I don't have a specific example, but so there might be a word that if you pronounce it literally, it's not the right way to pronounce it based on pop culture, what happened yesterday, right? So some kind of new.
I can give you an example. I can give you an example. ChatGPT, for example. Okay.
Yeah.
ChatGPT, for example, again, if I will write it as chat in capital G, capital P, capital T, probably the algorithms will know how to pronounce it. But if I write it in small letters, probably it will miss it. It will miss it.
Yeah, that's a good example. Yeah.
Okay. Just a second. Okay. So let's talk a little bit about speech-to-speech. And again, just to set the stage, when I'm talking about speech-to-speech, I'm not talking about what we call the classical evolution of speech-to-speech, what we call that open AI and what we call voice agents. When you have source, you're creating some kind of a speech recognition, converting that into words, and then synthesize that. And this is what a lot of the industry are calling right now speech-to-speech, because again, it's very natural to call it that way. I'm using there is a speech input and there is a speech output. What I'm referring to is mostly the things that you've seen in the demo. So basically, you have a speech input and you have a speech output, but you have some kind of a neural network in the middle that knows how to take a speech and convert that into another speech without going in through the word space. And
can you go back to the previous diagram?
yes, of course.
Oh, I see. I see. So basically, in this classical approach, you go source, and then it will have some speech recognition to convert it to words, and then another system that's text to speech, and then output.
Yes.
And then in this new approach, let's go to the new approach. New approach is basically source, speech recognition,
Without speech
transformer.
recognition. Yes, it's basically taking the best of two parts
Yeah.
and not going through the word space. It's
I see.
basically what you've seen in the demo.
So
Okay.
this, if you have to go through the word space, it's hard to make that real time.
It's hard to make that real time, and also think about that. If I want to take my voice, a lot of the things that I'm saying are not in the words. It's how I say that. Okay, in the tonality, in the emotion. So basically, again, like a lot of the things, if I'm going through the word space,
I see. Yeah. So it misses a lot then, huh?
it misses a lot. Exactly.
Yeah.
And again, going back to how we are thinking about the world, we are thinking that again, human conversations are not going to disappear. So if you want to augment human conversations using AI, using some kind of a speech-to-speech, you need to go through like what we call direct speech-to-speech.
Yeah, in many ways, this is a classic example of multimodality in the sense that if you just treat it as words, you lose a lot of meaning because there's another modality, the sound.
Exactly. The sound and the tonality. Exactly.
Yeah, exactly.
So think about, I'm always giving the example of, that people saying that you have like what we call the 55, 38, 7% rule, which is like, when I'm giving some kind of a presentation, 55 is in my 55% in the message is being transformed in the body language. 30% is how I say that. And only 7% is with the words.
Right.
So think about that while we are having a human conversation without video, it's like 84% of the message is just with how I'm saying things.
So can you, for us who are not following the space closely, Yishay, so what year was the transition between the classical to this new approach?
So a lot of, I think that again, like what we call, again, this is going, again, this is a great question. It's going to the next slide. And the first and like the first core technology is what we call voice conversion. Okay, and voice conversion, it's been existing for quite some time, but I think that up until the past, again, 2 or 3 years, it was not matured enough that you can talk about like actual conversations about that. And again, when you're thinking about voice conversion, okay, I have a source speaker, okay, and I want to transform the source speaker into some kind of a target speaker and to convert it. Okay, so basically, for example, like this is the source.
I've done nothing wrong, and that's the truth.
Okay, and this is the target.
He felt there was no case to answer.
Okay.
I've done nothing wrong, and that's the truth.
Okay, so you see that
that's incredible.
Yes.
Yeah.
Yes. So you see that the target speaker basically like so again, this is basically like some of the things you can think about. Like there are 2 types of technologies that you can do. One of them is take text to speech, transcribe that, and then put it into some kind of a text to speech using the classical voice cloning. But voice conversion tries literally to take some kind of a neural network that tries to know how to convert these things based on some kind of a characteristics. So
So this example you showed of voice conversion, if it's not real time, is that basically now available on open source? I mean, the
Yes,
non-real
yes.
time voice conversion is a commodity.
Yes, it's to some extent it's commodity. Again, it really depends if, for example, like if the source and the target speak the same language, if they have the same accent, like how long is the sample. But these things are more and more better
So
and
what
are very
so for a listener who wants to try this out, the non-real time version, so what systems should they Google?
Meta AI. They created a toolbox that is called VoiceBox and AudioBox.
Okay.
Great open sources. And again, I think that in the next lectures, I think that I'm addressing that.
I've done nothing wrong,
Sorry
and
for
that's the
that.
truth.
So yeah, actually, like this is the next slide. So if you're thinking about like Meta VoiceBox, it's a great open source that has multi-speaker TTS and style
Well, can
transfer.
you define what that means, multi-speaker TTS?
Oh, yes. So if you're thinking about it, multi-speaker TTS is the ability of a TTS to adapt to different type of voices. And again, this is what we call the core part of voice cloning. And again, this is what was the underlying thing of voice cloning. So think about like when in the initial phase that when I need to create a text-to-speech systems, I need to record, for example, let's say that I want to create a text-to-speech systems based on your voice then. This is what they call a single speaker. I need your voice in a high quality studio recorded for a few tens of hours. Okay? The problem that right now, for example, I don't know, I want a different voice and I want the text-to-speech system to sound like a different voice. It's a very challenging to get someone else, to go into the studio and to be recorded for a few tens of hours. So people have created what we call the multi-speaker TTS, which you are creating some kind of a system that knows how to be adaptable to different type of voices, giving short amount of audio input.
I see.
So basically, multi-speaker TTS is literally the technology behind voice cloning. Okay.
And this is since this is open source, have you seen people using this?
I think that for voice cloning,
Yeah.
I think that again, like it's I think that people are using that. I think that there are easier tools to use. For example, 11 Labs. It's again like the thing that with
Right.
open source is that you need to download the code, you need to make sure that it's workable, you need to and again like you have services that are much more easier to do voice cloning if you want.
Right.
So again, but if people are interested, from that aspect, I think that this is like one of the best open sources, and but there are probably more, but Meta VoiceBook and AudioBox are great examples for that. Now, before the last part, before we are going into what we call the ethics, I want to give you some kind of a glimpse of what we call LLM to speech in speech, and one of the things that people have done, and again, like we're all familiar with BERT, and so back in 2020, 2021, researchers have started to explore how can we take the techniques of LLMs and apply them to speech. And basically, if you're thinking about speech, again, like when I'm saying the word Ben or Yishay or I don't know, text-to-speech, we can think about these different type of unit of speech as some kind of a base units, and I can create an LLM that is just trying to predict the next base or the next phase of speech base units. So basically, one of the things that people have done is that they injected some kind of a huge speech corpus and just use the methods of LLMs.
So the classic LLM, which is the text in, text out system, you type in a prompt and then it starts answering by predicting kind of the most likely words, right? That you will want in an answer.
Yes. So basically, think about it that if you're even going one step back, it's a language model. Okay. So basically, the prompt is some kind of, the base of the language model, and I try to predict what are the next tokens.
Right.
So think about that a
No,
speech
but in the
language model.
in the context of your prompt, it will try to formulate an answer, and the answer is formulated by predicting tokens.
Exactly. So, for example, one of the applications of speech language models, speech LLMs, is that there are a few applications that you're, for example, trying to create some kind of, first phase of a music, and then the LLM will just try to generate another
Yeah.
set of music based
So
on that.
it's
So
the
again,
same kind of
it's exactly, yes, it's a very, very similar
predicting the
pattern.
next likely
Exactly.
token.
And instead of tokens of words, you're using tokens of speech. Okay. And I think that one of the most interesting things, and literally today, if you would ask me what's the most recent advances, the most hot topics right now in speech, is what we call neural codecs and neural codecs. And basically, one of the things that is happening with neural codecs is
So
that.
can you translate neural codecs in practical application terms? So what does neural codecs enable you to do?
So let's talk about even the simplest application.
Okay.
Let's talk about that. For example, I want to compress voice. And again, compressing voice it was a very well-known technique. For example, when I'm speaking with you over Zoom doesn't take my voice, it compresses it, it decomposes it into some kind of a codex and just transmit it over the web, because again, it's bandwidth and everything. And one of the things that when you're thinking about voice compression, I think that up until 2021, it was based on techniques from the 1990s a lot of the times. And the most recent one was some kind of a codec, some kind of a voice compression, which was called Opus, which was based on techniques that were developed in the 1980s, 1990s. And when you want to evaluate voice compression algorithms, you have two type of qualities. How good can you compress, and the audio quality. Audio quality we are measuring in, you can see in the table, audio quality we are measuring in some kind of a measure which is called Mushra or Morse. The higher is the better. And compression, we're just measuring with kilobits. Okay, voice is a very efficient medium. It's one-dimensional signal, so we're evaluating that in kilobits. And one of the things that you can see, for example, when these researchers try to apply Hubert, okay, so think about that, think about that Opus. If you see that in the middle of the table, it's some kind of, a decent codec, was invented in 2006 based on technologies in the 1990s, has around, I don't know, 10 kilobits or 10,000 bits per second, and it has a Mushra score of 70, which is pretty decent. And this is, for example, what we're experiencing right now. These Hubert-based compressions, they were around 10 times more efficient with the higher Mushra score. So basically, they were using so again, and this is, by the way, this slide is basically it's too old. Okay, and I didn't change this slide. So for example, if you're thinking about it, right now you have algorithms that are even better with higher quality. That is literally phenomenal. For example, over the weekend there was an algorithm called Wave Tokenizer, which basically is amazing.
So at this point, Yishay, neural codecs is in production.
Oh yes. To some, I think that there are, for example, some of the algorithms are in production. Again, if you're asking me what are some of the you have open sources, you have people who are implementing that. I think that again, it will take some years, for this technology to be evolved. But the good thing about neural codecs, and again, putting aside voice compression, that it created some kind of a new way to represent speech in a much more efficient way. And as a result, all of the things if you're thinking about when we are thinking about speech and representation, we always care about how we represent these vectors in a more efficient way. So these neural codecs open the door to represent speech in a much more efficient and better way, that you have text to speech. All the recent text to speech systems are based on these neural codec architectures. Okay, all of these recent voice conversion algorithms are based on these neural codec architectures. So that is why it's so exciting. And again, I've been evaluating the systems before and after, and actually, the performance is literally shocking how well these systems are working. Let me just, as a final example, again, before we are going into music and into ethics, let me just show you some kind of a nice clip of how can you apply some of these things to what we call emotion transfer. Okay, so basically we have some kind of an input of speech, and I want to transfer the emotion.
Yes, it was a man who asked, a stranger. It was a man who asked, a stranger.
Since then, some mysterious force has been fighting us at every step. Since then, some mysterious force has been fighting us at every step.
The fourth and fifth days passed without any developments. The fourth and fifth days passed without any developments.
So Yishay, these examples, right? So where you have the source is always neutral, and then the output has some emotion.
Mhm.
Is that being done in real time? No.
It can be done. Again, these are offline.
Yeah.
But I'm sure that in the future, again, like you can do this almost in real time.
Okay. So right now, for the sake of our listeners, a lot of speech-to-speech systems are not real time.
Yes.
But if your use case does not require real time, it's basically a lot of the tools are commoditized. Is that fair to say?
I would, again, like, if you're asking commoditize that, you have, companies who are doing that, that really depends on the use case and how commercial the potential of these commercial applications. But there are various open sources that you can find. And again, I would strongly recommend for people to check VoiceBox and AudioBox by Meta, because a lot of these things are incorporated into this open source.
Yeah.
The last thing that I just want to touch base, again, like we talked about music, and again, like music generation using LLMs is something that is becoming very, very interesting right now. There are different type of algorithms, different type of LLMs based on music, which is called Music LLM by Google or AudioCraft by Meta. Just want to show you, Ben, some kind of an example of how these things are working.
You know what? The most impressive thing in this example is actually the snippet around jazz, because the others, tend to be electronic music or beats and things, but the jazz seems like they're playing instruments, right?
Yes, and I think that, again, if you're thinking about music, there are so many things that you can do. You can generate different type of instruments, or given a prompt, you can create different type of models that are generating specific instruments and combine them together. You have so many things that you can do with that.
Yeah. And so the users of this kind of text to music kind of applications will mimic the users of text to text, the LLMs, in this following sense, right? So some people
Yes.
will use an LLM completely, right? So here's a prompt, write an article. Okay, this is my article finished. A lot of people will use LLM as a editor, right? So like here I write, improve it, right? Some people will use an LLM as more to generate ideas,
Mhm.
right? So basically, the same thing will happen here. The how people use it will depend on the person.
It depends on the person, and again, the different type of use cases. And again, when you're thinking about it, eventually, a lot of the applications of LLM today are for content generation, offline content generation. So again, you have the tools, and now you have different type of people who wants to take it into various aspects of that. As you said, one of them for generating new ideas. If you're thinking about maybe music, I just want to get new ideas for my next album, or maybe I just want to create an album. It really depends on how user.
Or I just need a drum track or something.
Yes,
Yeah.
yes. Sorry. The last thing, Ben, that I want to address, and I think that given all of the things that we have discussed, is something that is very important, is to talk about ethics and safety. And hopefully that in almost the last hour that we've been talking about it, is that we can understand that you can use these type of technologies in a very, very bad way.
And more importantly, we're not talking science fiction. These are tools that are available today. Except in some cases, real time may not be possible. Unless, for example, you work with Meaning, they can do real time speech to speech.
Yeah, but we are not gonna. Yeah, but we are not gonna develop we have very, very.
Yeah, they are very
based on that.
They have very targeted applications. Yeah, but
Yeah.
generally, if you want to do you do speech to speech, it's probably possible as long as it's not real time.
And in text to speech. So here's the thing. First of all, people actually use that, and there are various cases that actually people stole not just thousands but millions of dollars using deepfakes, using audio fakes.
Yeah.
So people are trying to impersonate and to call other people and again, like doing a lot of social engineering on people. And right now it's becoming much and much easier because again, when you're thinking about social engineering, now you have another medium that you can trick the persons because of the voice.
But if it's not real time, so one defense will be just to keep asking questions, because if it's pre-recorded and obviously it cannot interact with you, then that's one way to figure out, hey, this is actually not my real CEO, or this is not my actual CFO, right?
So you're spot on. And again, like when you're thinking about it, first of all, of course, like there are going to be algorithms that are built in order to detect that, and there is going to be huge market for that. But from that perspective, a lot of these things are related, in terms of educating people. Okay, a lot of the times, like when you're talking about social engineering, right now, we all understand that if somebody's sending you an email that says that he's from Nigeria and he just won a few millions of dollars, you understand that this is going to be a scam. Okay, because again, we know about these things. So a lot of these things in terms, again, and I'm putting aside that the use cases and the machine learning aspect of that, because this of course is going to be built, but just educating people that when somebody is calling you and is asking for something, you need to be assured that and to ask yourself, is it the right person?
Or you as a company may have to put processes in place to have multiple levels of authentication, right? So
yes.
Just because you get a call from the CFO, maybe there's many other checks you have to put in place in order to release $1 million, right? So.
Exactly, but there is a but. The other side of that is that you can get a call and somebody will not ask you for any money, but they will try to lure you to speak because they want to clone your voice. So that's another aspect that we need to take into consideration. Okay, because again, think about it. You're getting a conversation, from some kind of an insurance agent that want to sell you, an insurance, and you're just, luring you to speak for 15 seconds, and bang, I can clone your voice. Right. So that's something that we also I think that there are going to be applications to prevent to doing that.
So don't pick up the phone if you don't recognize the number.
Yeah, Justin. That's also yes. So there are a lot of risks.
So talk to us about the state-of-the-art detection tools, which I assume, Yishay, there's more money going into generation the detection. So the detection people are outgunned and outfunded. And obviously, it's also harder to play defense than offense, right? So.
To some extent, yes. But I do think that, so here's the thing, when you're it's like with every type of what we call cybersecurity, the more that people are seeing the threats, the more money that is going to be invested into these type of things and people that are going to be aware of that. And I've been living in that phase for, I think that, the past 6 or 7 years, and I've been always knew that these things are going to happen. So first of all, from a research perspective, you see a lot of data sets and a lot of papers and a lot of people who are addressing these type of things much more than they used to be. Second thing is that it's back, for example, 6 or 7 years ago, it was very hard to persuade people that this is going to be an actual threat, because again, they said, yes, it happens. I've read about it, but now when people see that this technology is commoditized, that how easy it is, then people are starting to understand that this is going to be a real threat.
So let me ask you this. So let's say, a thought experiment, right? So let's say that all the top speech labs, Meta, DeepMind, all of them decide, okay, from now on, we won't release code. We won't even publish papers that have too much detail. We'll just describe what we can do and have some online demos. So in other words, we're stuck with the tools we already have today, but we won't get any new open source tools from Meta, DeepMind, and all those people. I think
always
so. No. But my question is, do the bad, nefarious actors, even if everything stops today, do they have enough to work with to cause trouble for the next many years? So they don't get any more new updates. This is the best that the labs will release. I think they have enough to work with, right?
Yes, I think so. And again, you don't know, again, because of AI, it's a very theoretical question, because again, AI is evolving in such a rapid pace that maybe, for example, the detection algorithms of 2027 will, it will be very easy peasy to detect any algorithm that is based on 2024 technologies.
Right.
But one of the things that is happening is that, again, it's some kind of a debate. Should you do closed sourcing, open sourcing in every type of AI and AI technology? Because again, the open source, improving transparency, and people are aware of what are the risks and what are the things that you can do with that. And I assume that if it's going to be closed source, there are going to be research labs or people or bad actors who have the underlying technology to build very bad things on top of that.
Now, what's the state of the art? In other words, if I give you a piece of speech, can you say, hey, the probability that this is generated by a model is 40%?
It really depends if it's a black box or white box. If it's a well-known model, if for example this model was based on open source, if the model was not based on open source, the type of data. Usually, these algorithms, there are very good algorithms that can detect, but it's a cat and mouse game, because again, think about that. If I'm creating some kind of, I want to fool you, okay? I know that you are going to run some kind of a detector, okay? So my main aim, again, is I think that you think that you think that I think, okay? Is that I'm going to create some kind of a solution that is trying to fool your detector, okay? So again, it's a cat and mouse game.
Yeah. And just like in cybersecurity, it's much easier to play offense than defense.
Yes. And also, yeah.
So obviously, this is an election year here in the US. And that's why I keep hammering on this difference between offline and real time. So it seems like from this presentation, offline, there's many tools that you can use. So it should be very easy to do as long as it's not real time, deep fakes for audio, right?
Absolutely, and we've seen that. And I think that there was a case that somebody created the deep fake of President Biden, and there were some kind of a robocalls that pretending to be President Biden. So yeah, this is it's not that that theoretically people are doing that. The FCC, sorry, created like very, very strict rules against deepfake and against robocalls as a result of that.
So what's your thinking around closed source versus open source? Because this technology, as we described, right? So let's say in your case, you're not open source, and also you're building very, very specific types of enterprise applications. But what if someone is able to mimic your technology and make it open source? That's kind of so. What's your position on what people should be releasing at this point?
So I think that again, my opinion is that that we need to be very, very transparent. Especially, and again, I think that that Meta, by releasing Llama and by saying that again, the more that people are going to be transparent, we're also going to understand the risks. And I think that makes a lot. I think that
So
that
can
makes
you
a lot of sense.
describe, so in the case of Meta, DeepMind, what exactly have they released? Have they just released some tools so that you can use the system, or did they release the
They release also some models.
models, but just the weights of the models, not the training data, not the
Yeah.
right? So it's similar to what is happening in LLM. So Llama is open weights, not open source, right? So
Yes. And again, sometimes sometimes you cannot even release the data because again, you
but
cannot
can you
release.
take so is there the equivalent in this space, Yishay, I would imagine, just like in LLMs, fine tuning is basically a commodity, right? So is
To some extent,
fine tuning these models in speech also easy?
I think so. Again, I think that that the key part, and again, this is one of our theses, is that making that real time and making them very, very low latency is going to be challenging. Making them scalable, like to work on a very large amount of data that are very, very thin is going to be challenging. Building vertical use cases is going to be challenging, but the foundational models themselves, I think that they are going to be open sources, or the techniques, everything is Again, I think
Because you innovate both on the fact that you can do everything in real time, and then you have very specific use cases, and for those use cases, which I guess broadly speaking, one of them is in customer support, right? So
yes,
the accent softening in real time, but you also innovate not just on the real time dimension, but in the fact that you can deploy very efficiently, very
on scale.
scalably, and very cheaply, right?
Exactly. Because again, it's very different if you're talking about tens of thousands of people speaking for at the same time for multiple hours in a shift, rather than I'm just injecting some kind of a prompt and I want that the prompt will work like one day, or like 1 day in a month, like for 10 seconds. So it's very different.
Yeah. So in this case, so fine tuning an LLM, people understand what that is and why would you do it? Why would you do it, right? So in this case, why would you? I mean, I guess I asked you a question about whether fine tuning for these models is straightforward, but what would I now I'm struggling to understand why would I fine tune?
Yeah,
It's most. Is there a do people fine tune in this space?
Sometimes to other languages. Sometimes, for example, think that I have a very, very strong model in English and I want to for example, to train it for in Dutch.
Yeah.
Okay. So again, I'm taking like the core and just adding like, for example, 50 hours of Dutch, and I have a very, very solid algorithm for Dutch, for example. That's something that that people are doing. Think about it. You have you have like around thousands and thousands. I think 7,000 different languages in the world.
Right. And this has been great. And again, for our listeners, you may want to check out the YouTube version because this was a slide-heavy presentation. And to learn more about what Yishay and team are doing, go to Meaning.team. And with that, thank you, Yishay.
Thank you so much, Ben. It was a pleasure.